All right, let's go ahead and get started. Today's research presentation comes from Professor Yafeng Yin. Dr. Yafeng Yin's research interest is modeling and optimization of multimodal urban transportation systems for achieving efficiency and sustainability. His research has yielded more than 120 refereed papers in leading academic journals. Dr. Yin is the editor-in-chief of Transportation Research Part C, Emerging Technologies, Department Editor of Service Science, and Associate Editor of Transportation Science. He was elected to serve on the prestigious International Advisory Committee of the International Symposium of Transportation and Traffic Theory, ISTTT, in 2017. Dr. Yin received his PhD from the University of Tokyo, Japan in 2002, his master's and bachelor's degrees from Tsinghua University, Beijing, China, in 1996 and 1994, respectively. Everyone, let's welcome Professor Yafeng Yin.
So thank you, Calvin. Good afternoon, everyone. Thanks for your interest in my talk today. So in the following, I'd like to introduce you one of our recent research on how to leverage machine learning to transform the transportation network equilibrium analysis framework. So before I think this talk might be more technical than some of the talk that you heard from in this symposium, because I'm going to present quite a number of equations. For those of you who are working in network modeling, the equation will be similar, will be familiar to you. For those who do not working in these areas, and you don't have to read the notation of the equations and also try to make sense of the equations. Okay, so please just follow what I have to say. And then hopefully, I believe you will get the key points of our proposal. Okay, so, but before I start, I would like to thank my collaborators, and Zhichen Liu, and she is one of my PhD students. Zhichen, please stand up. Thank you. So Zhichen really, she spearheading of this research. So therefore, if you have any question about the technical detail of the implementation, please save those questions for her. And yeah, I will be able to answer, hopefully I will be able to answer other high level and picture questions. And then also in this research, we work with two researchers from GM, Dan Grimm and Van Bai. So working with GM allow us to get access to their trajectory data, which will allow us to do empirical study. The empirical study is ongoing, so therefore today the case study I present will be based on synthesized data, but hopefully next year I can present something from those empirical analysis. Okay. I also would like to take this opportunity to thank CCAT for the continuous support to my research program. Okay, so this is the outline of my talk today. So for this audience, I would like to give a very quick overview of the transportation network equilibrium analysis paradigm. And then we will discuss why we still want to transform this paradigm and how we're going to transform it. Okay, I'm going to use a simple example to demonstrate the proposal, and then I will finish by some conclusion remarks. Okay, so I think many of you understand that the transportation network equilibrium modeling paradigm play a very important role in the planning and operation of transportation networks. Because in practice, very often when you try to improve the performance of the system, you have multiple plans, and you need to compare those plans to choose the better one to implement, right? So in this paradigm, the notion of equilibrium really provide a benchmark or reference point against which the plan can be compared. More specifically, you assume that the status quo is at a steady state, which is the equilibrium. And then you, with plan, let's say, assuming you have two plans, you're going to assume that you're going to estimate the network performance under plan A at its steady state or equilibrium state. You also estimate the network performance under plan B at the equilibrium state, and then you compare them. So this ensures apple-to-apple comparison, okay? Because once you implement a plan, there may be multiple outcomes, but we compare against equilibrium state, okay? That's the key point. So equilibrium really, the notion of equilibrium provides a reference point. So the notion of equilibrium was first proposed by John Wardrop in 1952. That's the reason why sometimes we call this concept as Wardrop equilibrium, which refer to a state where no traveler can improve their utility by unilaterally changing their travel choices. Okay? So the Wardrop equilibrium actually is a Nash equilibrium with infinite number of players. Okay? So Wardrop Nash was proposed, Nash equilibrium was proposed by John Nash in 1950. So when Wardrop proposed his notion of equilibrium, I'm not so sure whether he actually understands or realized this connection. Okay? So, but if you look at Nash is about interaction between finite number of players. So when the number of players become large, computing Nash is very, very technical challenging. But if you look into the limit, when the number of players become infinite, computing Wardrop turns out to be much easier. As easy as solving, for some situation, solving a convex program. For example, if you're concerned about route choice, and also in this case, the trip generation choice, and then you can compute Wardrop by solving this formulation proposed by Beckman, McGuire, and Winston in 1956. I think virtually every student, translating student in the audience, you have learned about this formulation from textbook and in your classroom. Perhaps the version you learn, you don't have the second component in the objective function, right? You have, that's in the fixed demand situation, you only have the first component of objective function, and in the first component, the integration of the linked travel time function minus the integration of the inverse demand function subject to some liquid flow conservation constraints. So that's the formulation you learn from textbook. So as I said, virtually every translating student actually learned about this formulation. But I hope when you learn about this formulation, your professor will tell you that, okay, do not try to interpret the objective function because the objective function is simply a mathematical construct. The reason why the objective function takes this form is because if you write out the KKT conditions, the optimality condition will be essentially the equilibrium condition we define, which is all the utilized paths have the same travel time, which is going to be less than equal to the unutilized path. The realized demand will be given by the demand function with the equilibria or minimum OD travel time, right? So this is the formulation. But if you really want some physical interpretation of these objective functions, so here you are. The objective function really, because this game is a potential game, the objective function is a potential function for the potential game. So, okay. But even for potential function, you don't have a physical interpretation. But if you assume that, okay, if you consider a dynamic system whose steady state is equilibrium, Wardrop equilibrium, and then this objective function essentially represents the potential energy for the dynamic systems. Okay, if you really want a physical interpretation of this objective function. Okay, so now, since 1956, and this formulation has extended by many, many researchers, including myself, Professor Henry Liu in the audience, to model other travel choices and to capture within-day and day-to-day traffic dynamics. So this really is a seminal work, laid out the foundation for the paradigm of transportation equilibrium analysis. So to recognize the contribution of the authors, in 2005, at the Inform's annual meeting, so there was a special session organized to celebrate the 50th anniversary of the publication of this formulation, the BMW formulation, Beckman, McGuire, and Winston. So standing right in the middle is Professor Beckman, and standing next to him is Professor McGuire. At that time, Professor Winston has passed away. So 2 months this photo was taken, Professor McGuire passed away, and in 2017, Professor Beckman passed away. And if you can recognize, I'm the guy standing at the second line. So look at what network modeling did to me. At that time, I was assistant professor, just started at the University of Florida. I still had hair. So my point is, a lot of us have devoted our time and to advance this paradigm. And the paradigm is being used to plan the highway system, transportation system around the world. It's working well. So why we still want to transfer it, okay? Why we still want to do the transformation? So there are many reasons we do that, but today I just want to motivate from one perspective, which is enhancing behavioral realism. So if you ask ChatGPT, why do we want to transform narrow modeling equilibrium paradigm? So the answer provided by ChatGPT is going to be like this. Okay, you want to, the model, the travel behavior, choice behavior are much more complicated than what's assumed in the BMW model. Because when you learn the formulation, your professor is going to tell you that the model makes a very strong assumption about the behavioral, the choice behavior, right? So people have perfect information, they only care about travel time, they are maximizing their utility by choosing the shortest path, right? They have perfect information. So they're perfectly rational. But you can argue that the behavior observed in reality are actually much more complicated, right? So in addition to travel time, people may care about other factors, and some of the factors cannot be observed, right? For those unobservable factors, if you assume they follow certain distribution, then you can use discrete choice model to model those choice. And then if you encapsulate the discrete choice model into the narrow equilibrium analysis, then that gives you a class of stochastic user equilibrium model. So there's so many models in that category. But those models, within this model, the users are still utility maximizer. They're still maximizing the utility, even the utility are stochastic, but they're still perfectly rational. But if you assume that people are not perfectly rational and you want to consider those type of boundary rationality into the equilibrium analysis, then you forget the so-called boundary rational user equilibrium model. Okay? So significant effort has been made to try to enhance the behavioral realism of the narrow equilibrium model. The key issue here is, if you look at the literatures, all the model were constructed using a bottom-up approach. Okay? It's about how they build this model. Okay? So the process goes like this. You have to pre-select a behavioral model to begin the process. So let's assuming you're sure, hey, I try to use multi-luminal logic model to model route choice. So you have to start from this assumption. I'm going to use multi-luminal logic model. Okay? So once you make this pre-selection, and you just say, hey, assuming everything behaves this way, what's going to be the subsequent equilibrium condition, steady state? So you have to conceptualize that, and then you convert that into mathematical equations, right? So the second step will be, you have to conceptualize if everything behaves this way, what's the corresponding equilibrium conditions? Then you write mathematical equation to describe that conditions. The condition typically will be a nonlinear system, and sometimes will be nonlinear complementarity system very often. That system is difficult to solve, and then the next step will be, can I convert that system into an equivalent mathematical program or formulation such that I can solve that formulation more easily? The next step will be, you're going to convert that definition into an equivalent mathematical program, or chances are equivalent mathematical program do not exist, then you have to convert into a variational inequality. So the variational inequality will be, okay, will be the inner product of the past cost and the feasible equilibrium past flow minus feasible past flow minus equilibrium past flow. The inner product is non-negative. Okay, so this past cost will take different form when you have a different behavioral assumption. If you assume that, okay, we're going to choose, if the user are choosing the minimum path, if user are only care about travel time, they're trying to minimize, choose the shortest path, and then this is going to be the past travel time. So this is going to be the past travel time. But if you assume that, okay, we're going to follow the multinomial logic model to make the choice, and then, so this will be the past travel time plus an entropy term. So my key point here is, if you make a different behavior assumption, and this past cost function will be different. So your choice preference will be reflected by this past cost function. Okay, so then if you solve this VI, you can prescribe the equilibrium flow distribution and travel time. So now if you have some empirical observation of the flow and travel time, and then you can do calibration. So you can calibrate for this case. There's a dispersion parameter theta that you can calibrate by comparing the estimated travel time against the observed travel time. That's how you can do the calibration, right? So the problem of this process is you have to start with a particular behavior model. Okay, in this case, I assume that I'm going to start from multinomial logic model, which begs a question, why you have to use this model? Because there are so many other behavior model which was proposed by the behavioral scientist and economist. Okay, there's so many other models there. For example, even you use multinomial logic model, I can say, why not use probing model? Why not use C-logit? Why not use Weibit? There's so many different type of model you could use. Why you have to use multinomial logic model? Okay, so that's the questions. Because with different behavior assumption, you will have a different equilibrium conditions, and you will have a different formulation which give you different accuracy and predictability. So why you have to choose this model? So the choice depends on your belief. You believe this is the better model, but you don't really have, okay, the choice really is not data driven. Okay, that's the key problem. So the key issue here is the selection of the behavior model is not data driven. You only make the selection once you have the model, you do calibration. So the calibration comes after you made that choice. But why you make that choice in the first place? You made that choice is just because you believe this is a better model. Okay? So the selection of the behavior model reflects the modeler's belief and judgment rather than being the outcome of a calibration process against empirical data. The selection is divorced from the end goal of the model building, which is to prescribe an equilibrium flow distribution that matches observation as closely as possible. That's the key issue. That's the reason why that's the limitation of this model building approach, okay, which is bottom-up approach. So how are we going to transform them? We're going to move away from bottom-up to end-to-end learning. Okay? So to facilitate the presentation of our proposal, so let's consider a simple case where you want to construct a static traffic assignment model for peak hour, for peak period, and then we're assuming that I'm modeling a freeway system with tolling gantry. So therefore, I can observe the on and off flow, which is essentially I know the OD demand. I can observe OD demand. I can also observe the travel time because I have the tolling gantry data, right? So also assume we have all the link performance function. So therefore, the only learning task is I have to learn the traveler route choice preference from the multiple data observation of the link travel time and also demand. Okay, so that's the situation we're talking about. And because the static model, recall the variation inequality I was introducing, and you have the inner product, the cost functions, and the feasible path flow minus equilibrium path flow, the inner product is non-negative, right? I mentioned that if you make a behavior assumption, that assumption will be reflected by this cost function CH, the past cost functions, right? Different assumption leads to different cost function, but you have to in the bottom-up approach, you have to make a pre-selection, and then that give you a specific functional form for that past cost function, right? Multi-normal logic model will give you past travel time plus entropy term. So our proposal is, instead of making pre-selection, we're going to use neural network to approximate this cost function. And because neural network can approximate a lot of functions, so therefore, this will allow us to achieve a much richer representation of route choice preferences. Okay? So for the neural network, and certainly you have some input, right? The input going to be some context information, assuming that the neural network is trained, so which means that you know the theta, you know the weight of the neural network. If I give you context information, and if the network is trained, so you should be able to get, certainly the cost function will depend on the flow because the flow reflect the congestion level, right? So if I input the flow, and input the context information, if the network is trained, you should be able to get the past cost. Okay? So that's what we so-call neural network-based VI formulation. Okay? So now allow me to elaborate how the neural network will look like. So we assume that we have two neural networks. One we call attribute nets, which learned about the feature that user consider when they make route choice. Imagine you make a route choice, you may consider travel time, road condition, number intersection along the way, even the number of left turns. Consciously, unconsciously, you think about a lot of factors come into play when you make that decision. We're going to learn about the features. We're going to learn about, based on those features, we will learn about attributes that impact your choice, consciously, unconsciously. And then because you have multiple attributes, and then we're going to have to compute the weighted sum of those multiple attributes. We're going to have to convert them into one single cost, right? So that's the reason why we need the second neural network, which we call weight-net, which compute the weight associated with each attribute you learn, summing over those multiple attributes with the weight that give us the cost function. Okay? So the past cost is the weighted sum of the attribute you learn. The weight is learned, the attribute are learned. Okay, so in terms of the specific architecture of the neural network, you have a lot of flexibility. So if you're concerned about the interpretation of the behavior you learn, you could use some of the so-called physics-informed neural network that some of the researchers proposed recently because they try to combine discrete choice model with neural networks. So I call those as physics-informed neural networks. You could use them architecture. If you only care about accuracy, you can go with totally model-free, and you can use whatever the architecture you think can best reflect the situation, get the best outcome. But there's one thing you have to pay attention, which is you have to really ensure the cost function to possess some desired property. Sometimes you will have to use regularization techniques to ensure the cost function to be continuous to be Lipschitz continuous or to be monotone. If you want to ensure the past cost, the equilibrium flow distribution is unique, then you really have to use that, ensure that monotone property, which you're going to use some regulation technique. The more regularization you do, the more flexibility you will lose. So that's trade-off you have to make. Okay? And second thing you have to consider will be when you construct that neural network, you really have to think about, because the tendency is going to be I have different passes, and I just use those current neural topology. I can build a neural based on the current neural topology. But once we train the model, we're going to predict the future, and the neural topology is going to change in the future. The design of your new neural architecture will have to accommodate the change in neural topology in the future, because in the what-if analysis, I could remove a link, I could add a link, I could convert two-way street into one-way street. So you have to consider all those possibilities, right? So that's something you have to consider, even the challenge you have to overcome when you design the architecture of the new network. Okay, so once you have this new network, and once the new network are trained, so that's how the process goes, the so-called neural network-based network equilibrium analysis. So you start from, so there's a, so the input will be the traveler characteristics, okay, their destination. If you have information about the gender or other income, then you can use it. In our empirical analysis study, we use the car, the type of car they're driving, okay, which is data we can have. So whatever you have some feature about the traveler, we're going to be input to the VNet. You also have some network features. I mentioned the zero condition, the length of the road, and the capacity of the road, etc. So those are the road network feature at the input. And then you have a demand observation I mentioned. So then for the attribute net, so you have those side feature, and you have the pass flow. The reason why pass flow is the input to the attribute net, because some of the feature will be flow dependent. I mentioned travel time is flow dependent, right? So once you have that, that's going to be, you learned about, you have the attribute at the output of the network, because network are trained. You also have the weight net. The output will be weight. Summing over, you get the cost functions. If you have a pass cost, you have a pass flow, you can easily tell whether the equilibrium conditions are satisfied or not. If they are satisfied, you get equilibrium, you output that equilibrium flow distribution and travel time. If not, you have to do a fixed point iterations to adjust the flow, okay? So in the process, we're going to use computational graph to implement this process. And so the key point here is, the key challenge here is how you do the fixed point iterations, right? The different way you can do so. And you have to ensure that computationally, you can actually use computational graph to do the implementation, and the computation has to be efficient enough to solve this VI formulation, okay? So now this is essentially about when you want to train the network and how you do the equilibrium analysis. And the question is, how do we train the network? That's where the end-to-end learning comes into play. So in this end-to-end learning framework, at one end will be the inputs. You have a demand observation for multiple days. In the example, let's assume you have 3 days observation, but you should have many days observation for the training. And then the context information about the traveler and the road network will be the input. This one end. The other end will be you have some observed flow travel time information, okay? Some observed travel time. So then I mentioned about the VI formulations. And for an initial set of weight, and then you should be able to solve that neural network-based VI to prescribe the equilibrium flow distribution. And then that's how you estimate the equilibrium travel time and compare with the empirical travel time, and you can define a loss function. The training will be how can I adjust the weight to reduce the loss, right? So you have to do backward propagation to compute the derivative of the loss function with respect to the weight. And then you can use, for example, gradient descent to adjust the weight. So that's how you do this training. Okay? So that is the training. And now the training process, you have forward propagation. The forward propagation is about computing a bunch of AVI to estimate the equilibrium link travel time. Once again, compare the estimated link travel time with empirical link travel time, you can have that loss functions. The backward propagation is compute that gradient, and you can use gradient descent to adjust the weight, right? So the whole process, in essence, is to solve a mathematical program with equilibrium constraints. And so your decision variable is going to be the weight of the network, neural networks. Object function, you want to minimize that loss function subject to the loss function is the function of the equilibrium path flow, which is the solution of the VI, right? And then you have that, that's how you, then the second one is from the equilibrium solution, flow distribution, how I estimate the equilibrium travel time, right? So that's the, essentially, the problem is a mathematical program with equilibrium constraint because the VI here is served as a constraint for the problem. So now, this is a good time for me to make some connection between this proposal with some of the previous work in the literatures. So the first one is, if you get rid of the equilibrium constraints, then the learning problem become the so-called neural network-based traffic flow prediction. Okay? So if you recall, some in the literatures, some people have done that, because you have the flow observation from the field, from the network, multiple days observations. You also have the context features, and then you can create a mapping between the context feature with the flow observation using, for example, graph neural network, right? That people, many researchers has been doing this. So this is we call short-term prediction, because the underlying assumption is the environment that generates the data now you use for training will be the same as the environment that generates the future flow distributions, right? So the environment are the same. The underlying distribution are the same. So that's why you're doing in-distribution prediction. So for short-term prediction, this is okay. This assumption can be made because you're doing short-term prediction. You believe that the future, the demand will remain similar, and the network remain the same. But here we talk about the planning practice. We're planning for the future system in 10 and 20 years. So in 10 and 20 years, you may have to change the network topology, which create a new environment. So essentially, the underlying distribution will be different, and you're doing out-of-distribution prediction. So how can we do the out-of-distribution prediction? So essentially what we're doing is, instead of creating the mapping between the context information and the flow distribution, we are actually put the people into the picture, and we're essentially learning the travel choice preference, and our assumption is whatever travel preference we learn remain the same in the future. Okay? So we learn the travel choice preference from today's data, and we use that to predict the future. So that's a key assumption. Okay, implicit assumption we made in our proposal. Okay? So essentially, instead of learning the mapping between the context information and the flow distribution, we put a layer in between, which is we want to learn the choice preference. Well, we assume the system is going to be at equilibrium state. We use that preference to prescribe the equilibrium state. Okay, so that's the difference between our proposal with the short-term prediction based on neural network. Secondly, if you design a neural network in a certain way, I mentioned that you can use neural network to replicate virtually every discrete choice model, right? if you design the architecture in a way to replicate multinomial logic model, and then the problem become the parameter calibration work I mentioned in the beginning that, okay, I can calibrate the dispersion parameter theta if you design a neural network in a specific way. Okay? So that's a connection. So what's the challenge you have to overcome in the training process? Is because I mentioned this is essentially on the surface, you do this. It's similar to what you're doing for training the regular neural network. You have a forward propagation, you have backward propagation, right? You do that. It's similar. But for the forward propagation, notice that we're going to solve a bunch of VI. So the VI essentially, if you think about general neural network, the network, each layer is explicit. And if you compute the forward propagation, then that is easy to compute. But in here, I have a layer we call implicit layer, which is fixed point of VI. When you propagate through this layer, you have to solve this VI. And we still use computational graph to solve the VI, but you have to ensure that a specific way you solve the VI can facilitate the implementation of the computational graph to solve the VI efficiently. So that's for the forward propagation. The backward propagation is, remember, if you have a regular neural network, you can do automatic differentiation. But here, you have to really differentiate through this fixed point of the VI layer. That's the challenge. So then you really have to compute, right? So when you have to, the automatic differentiation does not work anymore. And so then you have to use, for example, in this case, we can use implicit function theorem to compute that derivative. But there are also other techniques you can use to compute, to do the backward propagation more efficiently. Okay? So that's the two challenges you have to overcome in the training process. In the interest of time, I won't elaborate how we overcome these challenges, but we have some way, but this is something we continue to work on to improve the computation efficiency, the training efficiency. Okay? So now I think it's a good time for me to just use a simple example to demonstrate the proposed idea. So I mentioned that we use synthesized data. Once again, we use our old friend, Sulforce network. It's a benchmark network everybody uses because it's very small. Okay? 24 nodes, 76 link, and 528 OD pairs. And also, because we don't have a ground truth, we just assume a pretty weird function, which we use this function to solve the UE to generate the training data and test data, right? And certainly this weird function is unknown to our learning framework, okay? And then we're going to compare our learning framework with two benchmarks, and one is UD equilibrium, traditional UD equilibrium formulation, the BMW formulation. The other one will be the SUE, logic-based SUE. For the BMW formulation, there's no calibration need to do, right? So, and then for the SUE, you have to calibrate that theta. We've done that calibration using the training data as well. Then we compare with our learning approach. And now we train neural network. We have actually 142 parameters you need to calibrate. Computationally, definitely more demanding. If our proposal is correct, if we design our framework properly, we should outperform the UE SUE, okay? So this is just to demonstrate the proposal is correct. It doesn't, we're supposed to outperform because we have so much more parameters to calibrate, right? So now, let's look at the results. We look at different type of demand, base demand, uncongested, congested, and we also look at, so we use the deterministic BMW formulation as a benchmark, and then compare with SUE and our learning framework. SUE in this case, we first do the so-called in-distribution test. You do the training for the same network. You do in the original network, you do the testing at the same network. We call it in-distribution test. So then the SUE outperform UE by 18%, and then our learning framework outperformed by 61%, improved the accuracy by 61%. This is in distribution test. For out of distribution tests, we do the training at the original network. We do the testing on a network whose topology has changed. Okay, this is out of distribution test. In this case, interestingly, SUE actually performed worse than UE, but our learning framework continued to outperform, improve accuracy by 55%, which only demonstrate the proposed idea, the proposed framework is promising. Okay, certainly more computationally demanding, continued effort should be made to improve that training efficiency. Okay. So this is my demonstration of the example, and then I have a few remarks before we finish. The first one is the major takeaway about the proposal. The centerpiece of a proposal really is to use the new network to represent the choice preferences, right? So we do not pre-select any particular behavior model. Instead, we try to learn them from data. Learn them from empirical aggregate link flow data and link travel time data. Okay. And we propose a new network-based VI formulation to prescribe the equilibrium flow distribution and travel time estimate. And then we encapsulate that VI into a end-to-end learning framework such that the new network can be trained by comparing the estimated estimate against the empirical data. So that training process gives you a learned new network that represents the choice preference. More importantly, the output of that learning process gives you a equilibrium state you learn from the empirical data. Remember, in practice, in reality, the system never settles into equilibrium. The data we observe are not equilibrium flow distribution. So essentially, you have to learn a particular equilibrium state that represents the status quo, and you use it as a benchmark against which the plan can be compared. Okay? You have to learn about those equilibrium states from empirical data. You cannot simply use empirical data as equilibrium state. Okay? And also, I introduced the framework using root choice preference as example. The question is, can the other component be learned in the framework? You have a demand function you should learn. You have link performance function you should learn in addition to those type of choice preference, the cost function, right? Theoretically speaking, you have a sufficient data, you have sufficient computational power, everything can be learned. But the problem is, we always have limited data, we always have limited computational power. What are we gonna do? Here's my suggestions. So you should use the domain knowledge to determine the model-based component and pre-calibrate them whenever you can. And then leave the rest to the end-to-end learning framework. Okay? So I believe that's, if we really go with this approach, that's gonna be the future. And also I use static assignment as an example, but can this framework be applied to dynamic traffic assignment? Yes, but we haven't tried that yet, okay? This is something we're gonna look into. So, and we just recently published the work I presented, and we published at TRPC. And so if you have interest in some of the detail, please refer to this paper, okay? So lastly, I have some remarks to the students in the audience. I think a lot of things you learn from the textbook were established like in 1960, 70, or even 50. So that was a time that was insufficient empirical data and computational power. But with that condition and our profession, our predecessors, they established the framework and they continue to improve that framework. The framework is working reasonably well in practice. But we shouldn't take for granted, because that was established many years ago, 60, 70 years ago. I cannot imagine we're going to use the same framework to plan the future connected automated mobility system. So I think we need to trace back to examine how those paradigm was constructed in the first place. And because they have a lot of limitation, a lot of data limitation, that's the reason why they create that paradigm in such a way. So you really have to understand why they're the way they are. And also think about the limitation associated with the current paradigm, and think about how we're going to leverage AI and also the advancement in computational power to transform those paradigms. I think it's your responsibility and your opportunity, because you cannot rely on computer scientists to come to do the transformation, because that transformation has to come from you with a deep understanding about the domain knowledge, okay, deep grasp of the domain knowledge. Okay, so with this, I conclude my talk today. I will be happy to answer questions if you have any. Thank you. Yeah, can you come to the podium?
Oh, so everybody come out. Okay. All right, there you go. At least I can break something. Rather than a question, I guess I just want a few comments. I think a very good approach, and especially the last part, very important. In mentioned about the technology, the time change, the technology change, and that opens up a lot of opportunities to really look at some traditional approach in a different perspective. But I just want to make some comments. First, you use a neural network to calibrate parameters, yes, especially those weights, okay? Now, compare this approach to the traditional approach. Traditional approach, at least we have, first of all, built some principles, right? Users, every user from your individual psychology, you want to optimize your individual time. At least, or there's like a choice specific, you have at least some basic economic models as a base. And then we build from there, make some assumptions, and then we develop the different, the old traditional type of models. By using the newer model and the newer approach, the neural network to calibrate the parameters. Let's hold it. I thought my sound, I have an energy problem, but I should be loud enough. The only drawback here, I say, compared with the traditional approach is, again, is it just a comment. Finally, you think you have a calibrated model, okay, all right? And then, can we make sense of those W's, those weights? Just one example, one set of parameters. The physical meaning to engineers, for us, even scientists, become more and more important, because this can help you avoid making huge mistakes in the future, especially something can, happen quickly and the consequences are large. If we can build this link to interpret what those parameters mean, physical meaning of those W's, right? I mean, we give you a whole set of data, okay, to do the training, fine. But first of all, we have to guarantee the data has to be realistically reflect reality, right? What if one day there's some special thing going on, then the travel pattern, is not really representative. So of course, you can avoid that problem by using not only one day, multiple days, or we do some kind of testing and checking to see really the data set is representative, and it will go from there as possible, okay? So it's just like a comment on the importance of this calibrated parameter. nowadays with artificial intelligence, a lot of things can happen in a black box. You don't really know what's going on there. But it's good, but it's also bad. Something important, maybe critical things lost in order to avoid mistake, especially those ones that really matter. Maybe there is a link if we can develop, to interpret those parameters. Okay, anyway, that's my comment. One, and two, I guess I mentioned already in the process, the data sets you use there, because today's data versus maybe next week on the same time could be different, right? So if you do multiple times, if there's no problem, you can still find a very nice set of parameters to get this to work, then that'd be good news. But in the end, I comment Dr. Yin's work. I mean, this is a good approach. We take advantage of the computing power. A lot of things really what's happening there in the process. Really, I mean, in terms of make a quick decision, not as so important. But in the long run, we do need to know, right, the importance of the parameters.
Yeah.
I took
Okay.
too long.
Yeah.
I took it too long.
Thank you, Professor Yi, for the comment. So this is the comment we get a lot in the review process. So first, I would like to respond to the first comment. Neural network is not a black box. If you want to make sense of it, you can actually design the architecture in a way you can interpret the weight. Okay, so we shouldn't blankly make a statement that, okay, if I use neural network and the trained model cannot be interpreted. That's definitely a misconception held by the people who don't have a good understanding about neural network. You should look into the literature to look at that a lot of work actually combine discrete choice model with neural network, and the results actually can be interpreted. And I also mentioned that if your intent is to have a good understanding about the behavioral insight you learn, if you want to make sense of the trained neural network, you should use that, I call it as physics-informed neural network, which has been developed by quite a few researchers in discrete choice model domain. So you can actually interpret them. And the second, responding to the second comment, which is, yeah, you use the data every day, the situation change because the demand could be different, the weather could be different. That's the reason why you observe different type of flow, right? So then that's the reason why you have the feature of the input to the neural network can be the time of day, a day of the week, for example, weekday and weekend, even weather is a feature to that. If you want to learn the demand function, okay, the demand function will depend on whether it's a weekday or weekend, whether it's the weather condition. We're going to use, for example, in our empirical data, we're going to try to use the amount of the snow and rain as a feature to learn the demand functions. So once you have sufficient data, certainly you can learn, but if you don't have sufficient data, then you're going to have the overfitting problem. So in that situation, I guess it's, once again, you can use some more domain knowledge, right, and approach. So I always feel that depending on how much data you have, and you can decide how much domain knowledge you use. And so essentially, the framework is pretty general to incorporate both model-based approach, or model-based component, and model-free component. So which one you use really depends on your modeling purpose and also the availability of the data. But I could argue that the proposed framework actually include the traditional approach, the model-based approach, as a special case. Because if you've, as I mentioned, I can design a neural network to replicate virtually every discrete model you want to use. And then essentially I incorporate those traditional SUV model as a special case. Okay, yeah.
Thanks for the talk. And going back to this model-based, or I believe you called it something else, neural network approach versus
Physics informed.
yeah, physics informed. There
Right.
we go. Yeah, physics informed neural network versus more of a black box approach.
Yes.
You mentioned that there could be some differences in performance.
Yes.
And can you speak a little bit more on that? What kind of trade-off do you see in your experience from the systems that you work with?
That's a good question. We haven't done that yet. And so in the empirical study we're doing, we're going to do those to see with trade-off, right? And essentially, one thing we're going to look at, and there are different components. Really, if you think about a narrow model like this, you have three major components, right? I mentioned demand side, the performance function, and also the cost function that reflect the preference. And so which part you want to use model-based approach, which part you want to use model-free, right? And which part you can use traditional. For example, I could use, for example, the choice preference if you are more comfortable with traditional discrete choice model, and I use model-based approach for that, right? The demand function, I could argue that, okay, I may use a model-free approach, right? I use neural network to approximate the demand function, right? So those are the trade-offs we will be looking at, and which part we use model-based approach, which part we use model-free approach, and how much difference make. Right now, I don't have a good answer, a very good question. I think it's also is about the training part is one thing,
Right.
but the prediction part is another story, right? I could look at, okay, the trade-off can be made just against the training data to say, okay, the training for training, and then whoever gives me the best accuracy, smaller error, smaller loss function can be the better choice. But that does not necessarily mean that the prediction is better, right? So yeah, that's something we definitely will look into. Thank you.
Thanks.
Yep, thank you.
Yeah, Professor Yin, thank you for the talk. So I have a question regarding to the why it needs to be separated into the. I'm still confused why it needs to be separated into feature net and the weight net.
Yeah,
Be-
yeah, that's a good question.
Yeah. The reason is that the first question I want to clarify is the feature has the physical meaning you get
Correct.
from the feature
Yes,
net.
yes,
Okay.
yes. I asked the same question for Zhichen. So I said, why you have to
Yeah.
sort of, okay, that's a good question. I also had the same question. So here, right?
Yeah.
So first of all, the features all has physical meaning. Condition, length of the path, number of intersections, payment condition, right? So those are the features. And then the attribute really, you can think about attribute is the combination of the features, okay? And attribute here is no physical meaning. Can be essentially a nonlinear transformation of the feature into, let's just say, utility function or disutility, right? And then after that, I could have weight to just sum them into a single cost. So why you have to separate weight net and attribute net, right? So just an answer is the attribute net in this case. First of all, her answer is if you look into the literature, the people who study the discrete choice model, right? There's people who actually work in discrete choice model. They try to use neural network, combine neural network with discrete choice model, and typically that's the structure they use. But secondly, she mentioned that if you notice that the weight net really inputs, the weight net depends on the traveler characteristics. The weight will be different for different people. Okay, the weight is different for different people. So the input to the weight net is only the traveler characteristics. The attribute, in this case, is neural network features. So that's how she separates these two.
Yeah, but since the attributes has no physical meaning, right?
Right.
So if you encapsulate this into a big black box neural network,
Right.
you input different traveler characteristics, you can still output different costs,
Right.
right? You don't need to tell like this traveler has this weight, that traveler has that weight. You can
Right. Yeah.
implicitly encode in it.
I believe so, but I think if you really want to have some behavioral interpretation, because you can change I can keep the weight net, I can change the attribute net to sort of have a behavioral interpretation about the weight. Because if that is important for you, for example, if I only have the travel time, right? If I design a new network in a way, and then you say, hey, my weight net can give you the value of travel time, for example. So the weight definitely sometimes, I think it's represent those type of sensitivity information that sometimes the behavioral scientist is very concerned about. That's reason why, I guess that's reason why they tend to separate these two, the weight net from attribute net. But for computational purpose, I think you can combine them into one.
Right.
All right, before we thank Dr. Yin, I would just like to say we're going to be taking a 15-minute break, and then after the break at 3:30, we will have another research presentation in this room on motion sickness, and then there'll be a panel discussion on freight electrification in the adjacent room. So let's thank Dr. Yin.
Thank you very much.